Oh, g'day guys, Mr. Bennett here. Today we're going to be looking at magnetic fields. So what happens here is we're going to be talking about current carrying wires. Now, it was discovered that if you have a current carrying wire, which obviously uses electricity, at right angle to that particular current, you have a magnetic field that's produced. Right? And we use a thing called the wraparound rule. Now, don't want to be discriminatory here, but all of the rules that we use for magnetic fields were developed for right hands. Alright, so you've got to use your right hand even if you're left-handed. So imagine if you were holding a wire with your hand and try to imagine your thumb's being directed upwards. So therefore, what you're going to do is, the first rule is called the wraparound rule. So the direction of your fingers will determine where the magnetic field is. As you can see on the left hand side of the screen over here, we've got the field lines going into the page there and coming out of the page here. Now that's really hard to draw, so what we use is the idea of a cross and a dot. Now if you think about an arrow has feathers at the end, right, which make like a cross shape, and at the point it's got an arrow head, and that's like a point. So this represents on this side here coming out of the page, and the cross means going into the page. Alright, so that's showing you where the magnetic field is for that. Hopefully that makes sense. Alright, to make an electromagnet, you can use a coil of wire, you wrap it around something, and we'll actually play around with some of those, and they're really quite powerful. It's very simple. Now, to know which end is the north end and the south end, I always have electric fields, magnetic fields, and so on together. You use this idea here. So if you make that shape there, that's a north, showing you the direction of the coil going that way. That's the north end. And if it's going the other way, you can see that makes an S, and that goes in the direction of that. So that's something to remember. Alright, so maybe put that on your formula sheet this year. Now the force for a magnetic field is equal to B, which is the magnetic field strength. We measure that in Teslas. I, which is the current, and the L, or the change in the length. So that's the length of the wire that you've got, and sine theta. Now this year, sine theta is going to be 90 degrees for most things, so therefore that's going to be 1. Alright. If the wire was at 0 degrees, in other words, this case here, the wire is in the direction of the field, there is in fact no force on that. Alright, it's only when it's perpendicular to the field, like in this case here, that you actually get a force directed on that particular wire. Rightio, so let's look at an example over here. If we have a field which has got 2 Teslas, that's a B, is the symbol for magnetic field, a length of wire which is 40 centimeters long, and it's carrying a current of 5 amps, then we would simply go 2 times 5 times 0.4. You have to put that into meters, so therefore it works out to be 4 newtons into the page. What does that mean? Into the page. Well, this is the direction of the force that you need to know. Now, what I want you to do is I want you to understand this little diagram here. Now, I'm not very good at drawing hands, but the I, or the current, is in fact your thumb. Okay, your fingers are all the field lines, and that actually, and then your palm, think about your palm being pushing out, so you're pushing on something with a force. So your thumb pretty well could be right angles to those fingers, and then the force coming out of your palm could be at right angles as well. I'll show you this in class because I think it's important to get that. So in this particular case, you put your fingers in the direction of the field, and that's going upwards, so you put your hand going upwards. You've got your thumb going to the left hand side, and so therefore you would be pushing into the page. So that's the direction of the force. Alright? Let's look at this example here. Okay, your current's going to the right again. Your field lines are in fact going into the page, aren't they? Right, so therefore that would be pushing down for this example here. Okay, if the wire was going with the field lines, there's no force at all. This particular one over here, this example, your field lines are going down. The dot means that your current's coming out of the page, so you're going to have your hand contorted a little bit, but that means that your force is going to get pushed to the right. I think this is something I'll probably need to show you in class more than anything over there. The field lines here, little dots are represented coming out of the page. Your current's going down, right? So therefore that would represent the force going to the left-hand side. Right, so there's some examples there. One of the key examples that we'll use, and I'll show you this in class, is a moving coil loudspeaker. With the RF there. So a moving coil loudspeaker has a little voice coil wrapped around. This is a permanent magnet. Okay, so what we're going to be looking at is the effects of that. So if we have our coil going in that direction there, alright, so therefore if you're looking at, that's the north part, that's the south part, so we have field lines going in this direction here. Alright, so we're using this right hand rule. If you do your field lines there, you get coming out of the page, that means you're going to have a force pushing up that direction there. Again, if you've got your field lines going into the page, you're going to get a force going up that way. So what happens is the moving coil loudspeaker, which is on a suspension, will push up that way. When we change the direction of the current in our moving coil loudspeaker, what happens is it causes the force to go in the opposite direction. And so therefore, by changing the current in a moving coil loudspeaker, will cause the cone to go back and forth as many times. So if you set the frequency of 10 Hertz, you would change that 10 times. Okay, 10 times a second. If you were trying to get a frequency of 20,000 Hertz, you would get the current changing direction in that moving coil loudspeaker 20,000 times a second. Alright? And so therefore, what happens every time it goes back and forth, you get these areas of compression and refraction, as we did talk about in our sound unit. So that is a very good example of using the force of the magnets. Okay, moving like a current carrying wire inside a magnet produces a force. Alright, so that's a useful application of that. Anyway, we'll talk about some more of this in class. See you for now.